Good evening. Welcome to Deep Sleep Manufacturing. Tonight, we invite you to step inside one of humanity's oldest and most continuous manufacturing processes, the creation of paper and its transformation into printed media. For over 1,000 years, paper has been essential to civilization. It carries our words, our art, our stories. And tonight, we'll witness the methodical, rhythmic process that transforms raw wood fibers into the printed pages that fill our world. Our journey takes us to a large integrated paper and printing mill located in a quiet river valley. This facility combines two related processes, papermaking and printing. The same machinery that creates the paper also transforms it into finished products. Nothing is wasted. Everything flows in a logical, interconnected sequence. But the journey begins not at the mill itself, but in the forest. For several weeks before our story begins, loggers have been harvesting trees from sustainable forests. The wood, primarily pine and birch, is cut into logs approximately 1 meter in length. These logs are transported via truck and rail to the mill. The first trucks arrive at the mill's receiving station at dawn. These are massive vehicles, each carrying dozens of logs stacked carefully to prevent shifting during transport. The logs are impressive. Some are 1 meter in diameter, some are smaller. Each one represents a tree that grew for decades before being harvested. A worker in a high-visibility vest stands at the receiving station with meticulous attention. He's holding a clipboard with a detailed checklist and a laser measuring device that glows with a soft red light. As each truck arrives, he records the load with precision. The vehicle's license plate is noted. The number of logs is counted individually. The approximate weight is recorded based on log diameter. Each log is photographed from multiple angles. The documentation is comprehensive and meticulous. Every log must be accounted for. Every log has a purpose. The worker communicates via radio with the facility supervisor, confirming receipt. Truck 1214 is arriving with approximately 80 logs. The receiving clerk reports into his radio. Diameter classification, primarily 60 to 80 centimeters. Estimated total weight, 340 tons. Copy that. Comes the response from the supervisor. Route to storage yard section C. Verify species identification. The receiving clerk examines the wood more closely, verifying the wood species. Pine is lighter in color with distinct grain patterns. Birch is slightly different in appearance. He makes notes. The classification is critical because different wood species have different pulping characteristics. They'll produce slightly different paper qualities. A forklift operator positions his vehicle beside the truck. The forklift is a substantial machine with industrial-grade forks. The operator positions the forks beneath the first log. The pronged forks slide under the log smoothly. The operator raises the forks slowly. The log, which weighs approximately 400 kilograms, is lifted effortlessly by the powerful machine. The hydraulic system hisses softly as the forks rise. The operator drives the forklift toward the log storage area. The movement is careful and deliberate. The log is balanced perfectly on the forks. The operator navigates around other equipment, moving smoothly through the receiving area. The path is predetermined and familiar to the operator. In the log storage yard, logs are carefully stacked in organized piles. Similar sizes are grouped together. Logs between 60 and 80 centimeters in diameter form one pile. Logs between 40 and 60 centimeters form another. The arrangement is systematic and efficient. The operator positions the log on top of similar logs in its designated pile. The log settles into place with a soft settling sound. The operator returns to the truck for the next log. The process repeats. Log after log is unloaded. The rhythmic operation, Drive forward, position, lift, carry, deposit, return, becomes hypnotic. Each cycle takes approximately 3 minutes. By mid-morning, the first truck is completely unloaded. 80 logs now rest in the storage yard. Another truck is backing into the receiving station. The receiving clerk repeats his measurements and documentation. The process begins again. Throughout the day, trucks continue arriving at regular intervals. The receiving area is a choreography of movement. Trucks arrive. Forklifts unload. Logs are stacked. Documentation is completed. Trucks depart. The rhythm is established and maintained. By sunset, 12 trucks have arrived. Approximately 960 logs have been unloaded, counted, documented, and stacked. The logs rest in enormous piles, organized by size and species. The logs are weathering in the setting sun, bark still intact, carrying the scent of the forest. Workers walk among the stacks, observing and recording information in notebooks. The logs will rest for 2 to 3 days before processing begins. This waiting period is not idle time. Quality control is critical to the papermaking process. The quality of the final paper is determined partially by the quality of the raw wood. Workers walk through the log storage yards during the evening hours. They're trained inspectors who understand wood quality. They examine logs systematically, moving from pile to pile. Each inspector carries a clipboard with evaluation criteria. An experienced inspector approaches a pile of large logs. He examines the bark carefully. High-quality logs should have minimal bark damage. Bark acts as a protective layer, and damage indicates potential problems inside the wood. He runs his fingers across the bark, feeling for soft spots or decay. This tactile assessment is as important as visual inspection. The inspector moves along the log, checking for visible defects. Cracks in the bark indicate potential internal splitting. These logs might be set aside for alternative use. Logs with insect damage, visible holes or tunneling patterns in the bark, are marked for rejection. These insects could have damaged the wood fiber structure. He examines the ends of logs where freshly cut wood is exposed. The color should be light and consistent. Darker coloring indicates oxidation or decay. He uses a small tool to probe the cut surface, checking for softness that would indicate rot. Quality logs are firm and hard when probed. The inspector makes notes on his clipboard. Pile C7, approximately 95% acceptable. Mark 5 logs for alternative processing. The alternative logs aren't wasted. They're sold to local timber companies or used for lower-grade purposes. Multiple inspectors work simultaneously through different sections of the storage yard. They develop a sense for wood quality through years of experience. They can assess a log's viability within seconds. Their judgments are documented and used to guide the pulping process. Premium logs will be processed separately from lower-grade logs, as they require different cooking parameters to produce optimal quality. The evening inspection takes approximately 3 hours. By nightfall, all logs have been assessed. The inventory is documented. The sorting is complete. The facility knows exactly which logs will produce the highest quality paper. As darkness falls, the log storage yard becomes quiet. The logs rest. The facility transitions to night operations, but the papermaking process has already begun in the minds of engineers. Tomorrow, the transformation begins. After 3 days of storage and inspection, the logs are finally ready for processing. The first step is debarking, removing the bark from the logs. Bark, while important for the tree, is not useful in paper production. It must be removed before the wood can be processed further. Early morning operations begin at the debarking facility. A log handler operator takes his position at a mobile crane. The crane is substantial, designed to lift and position heavy logs with precision. The operator positions the crane beside a pile of premium logs, those rated as highest quality during inspection. A log is selected and positioned onto a conveyor system. The log is placed horizontally on a moving belt. The conveyor system is designed to transport logs efficiently through the debarking machinery. The belt begins to move, advancing the log toward the debarking equipment at a controlled speed. Workers in hard hats and safety vests monitor the log's progress as it advances. They're watching for any irregularities, a log that's not positioned correctly, or any hazards in the path. The log moves steadily forward, and the workers move with it, maintaining their watchful positions. The debarking machine is a substantial piece of equipment. It consists of rotating drums with internal friction surfaces, essentially rough textured surfaces that can grip and remove bark. The machine is positioned over a collection area where bark will accumulate. As the log enters the debarking machine, it's gripped by rotating mechanisms. The log begins to spin slightly as it passes through. The friction surfaces contact the bark. The sound is immediately noticeable, a grinding, scraping, crunching noise as rough bark encounters the friction surface and is stripped away. The bark comes loose in irregular pieces. Some pieces fall away immediately. Other bark is more stubborn, and the friction must contact it multiple times. The log rotates slowly, ensuring all sides are exposed to the friction surfaces. The bark gradually accumulates in the collection hopper below, creating a pile of irregular bark chunks. The debarking process is not instantaneous. The log spends approximately 2 minutes passing through the machine. During this time, the friction continuously works to remove bark. The sound is constant, a grinding, scraping, rustling sound as bark is removed. The debarked log emerges on the other side of the machine, naked wood, pale in color, smooth to the touch. The bark has been almost completely removed. Workers using handheld inspection tools examine the log to ensure debarking is complete. They run their hands across the surface, feeling for any remaining bark. Any stubborn bark remnants are noted. Occasionally, a log exits with some remaining bark. These logs are sometimes passed through the debarking machine a second time, or the remaining bark is removed manually using specialized hand tools. The manual removal is tedious but necessary for logs that will produce the highest quality paper. Most logs, however, are completely debarked after the first pass through the machine. The clean logs continue on a conveyor toward the next stage of processing. The debarking machine operates continuously throughout the day. As one log exits, the next enters. The rhythm of the operation is steady. Logs arrive. Logs are debarked. Bark is collected. Clean logs depart. The operation has been refined through decades of operation to be efficient and consistent. The accumulated bark is transported via conveyor to a storage area. The bark is not waste. It has significant value. The bark will be used as fuel in the mill's biomass power plant, generating heat and electricity that powers much of the mill's operations. Sustainable operations depend on using every part of the wood. By midday, approximately 150 logs have been debarked. By the end of the day, that number reaches nearly 300. The pile of clean logs grows steadily. The debarked logs are ready for the next transformation. The debarked logs continue on a conveyor toward the wood chipping facility. The chipping station is an area of intense industrial activity. This is where logs are transformed into wood chips, the raw material that will ultimately become paper. The wood chipping facility has multiple chippers operating simultaneously. These machines are among the largest in the mill. Each chipper can process an entire log in just seconds. The sound of a chipper in operation is distinctive and dramatic. A log handler positions a debarked log into the feed slot of the first wood chipper. The log is guided by the handler using a long pole, ensuring proper alignment. The log must enter the machine straight and centered. Once positioned, the handler steps back to a safe distance. Safety is paramount. The chipper operator, sitting in a comfortable, insulated cab at a safe distance, watches the log enter the machine. The operator has a clear view of the feed mechanism through reinforced windows. The operator activates the chipper. The sound is sudden and powerful. The chipper's massive blade begins to rotate at incredible speed. The blade is a rotating circle of hardened steel, multiple meters in diameter. When activated, it rotates at thousands of revolutions per minute. The log is pulled into the machine by powerful mechanical fingers and guides. The log advances toward the spinning blade. The chipper operator controls the feed rate, ensuring the log moves into the blade at the optimal pace. The blade meets the wood. There's a loud crunch and crackle as the wood is cut into chips. The sound is mechanical and powerful, but there's a rhythm to it. The blade bites into the wood. Wood fibers are cut apart. The resistance forces the blade to work, creating varying tones depending on the density of the wood. The log is pulled through the blade continuously. As it passes through, it's cut into progressively smaller pieces. What enters as a solid log emerges as wood chips. The entire log is reduced to wood chips in roughly 30 to 45 seconds depending on log diameter. The wood chips fall from the chipper into a conveyor system below. The conveyor carries the chips away from the chipper toward the next stage. The chips accumulate in piles as they're deposited onto the conveyor. The sound of chips falling onto the conveyor is a pattering sound, thousands of small pieces landing with a metallic ring as they contact the steel conveyor surface. The debarked log, a substantial piece of material when whole, has been completely transformed into smaller chips. These chips are roughly 5 to 20 centimeters in length and similar in width, the optimal size for the pulping process. The wood chipper operators work in rotation. One operator feeds logs to the chipper. Another operator monitors the chip discharge to ensure the conveyor doesn't become overloaded. Communication is maintained via radio. Next log ready, the feeder calls. Conveyor clear, responds the discharge operator. The coordination is smooth. The chippers operate throughout the day without interruption. Log after log is processed. The rhythm becomes hypnotic. Crunch, discharge. The next log. Crunch, discharge. By the end of the day, approximately 1,000 logs have been chipped. The volume of wood chips produced is remarkable. Thousands of tons of material that began the day as solid logs. The chips are transported via conveyor system to a massive storage silo. This silo is an enormous cylindrical structure, approximately 15 meters in diameter and 30 meters tall. It can hold thousands of cubic meters of wood chips. The chips are transferred into the silo through an opening at the top. As chips accumulate in the silo, internal mechanisms, rotating paddles, distribute them evenly, preventing bridging, gaps from forming, and ensuring consistent material flow. The silo fills gradually over the course of multiple days. By the end of the week, the silo is full, containing approximately 800 to 1,000 cubic meters of wood chips. Workers monitor the silo level constantly. A sensor at the top indicates when the silo is full. Another sensor at the bottom indicates when material is flowing properly. The silo represents the buffer between the raw material processing, debarking and chipping, and the pulping process. If the silo weren't present, any minor disruption in the chipping operation would halt the pulping process. The silo provides operational flexibility and continuity. Before the chips enter the pulping process, they're subjected to quality control. The size and moisture content of chips are critical to producing consistent paper quality. Chips that are too large won't process evenly. Chips that are too small may process too quickly and incompletely. Moisture content affects the cooking process. Chips that are too wet or too dry will cook differently. A quality control technician approaches the base of the chip storage silo. He operates a sampling valve, a small opening that allows a small quantity of chips to be extracted. He fills a container with approximately 2 kilograms of chips. This sample is representative of the current silo contents. The technician transports the sample to the quality control lab. Here, chips are subjected to measurement and analysis. A series of sieve screens is used to determine chip size distribution. Chips are placed on the top screen and shaken by mechanical vibration. Chips of different sizes fall through different mesh sizes. The technician records how many chips fall through each screen. This provides a size distribution profile. Another test measures chip moisture content. A chip sample is weighed on a precision scale. The chips are then dried in an oven at a specific temperature for a specific time. Once dried, the chips are weighed again. The difference in weight represents the water content. Moisture content should be approximately 20 to 30% for optimal pulping. A third test measures the density of the chips. Dense chips indicate good wood quality. Less dense chips might indicate softer wood or wood with defects. The density measurement is performed using water displacement. Chips are immersed in water and the volume of water displaced is measured. This provides insight into chip quality. The results are recorded and analyzed. Most tests produce consistent results. The chip quality is high, suitable for producing premium paper. Occasionally, a batch of chips might show excessive variation in size or moisture content. In these cases, the operator adjusts the chipping parameters, blade speed, feed rate, or chip discharge, to correct the problem. Meanwhile, other preparations are underway in the pulping area. The digesters, the massive cooking vessels where pulping will occur, are being prepared. These are cleaned and inspected. Any residual material from the previous cooking cycle is removed. The digesters are tested for leaks and proper operation. Chemical supplies are verified. The sodium hydroxide, caustic soda, and sodium sulfide used in the pulping process must be available in sufficient quantity. Large tanks containing these chemicals are positioned near the digesters. Pumps and mixing systems are tested. Water supplies are confirmed. Cooking requires large quantities of water. Water pressure and temperature are checked. The facility's water treatment systems are operating to provide water suitable for the cooking process. Everything is ready. The pulping process is about to begin. The wood chips are now transported to the pulping facility through an automated system. A controlled amount of chips, approximately 3 to 4 tons, is directed to the first digester. This quantity has been calculated to optimize the cooking process and produce the highest quality pulp. A conveyor delivers wood chips into the top of an enormous digester, essentially a massive cooking vessel. This is a cylindrical steel structure, approximately 5 meters in diameter and 10 meters tall. The walls are thick steel, engineered to withstand extreme pressure and temperature. Workers at the pulping facility are dressed in protective equipment appropriate for working with caustic chemicals. Safety vests, gloves, and safety glasses are standard. Some workers also wear respirators as chemical vapors can be released during certain stages. Safety is paramount in a chemical processing environment. The chips fall into the digester gradually. A worker monitors the chip level through a viewing port, a small reinforced window in the digester's side. The worker watches as chips accumulate. Chips accumulating. Level at 20%, the worker reports via radio. Minutes pass. More chips enter. Level at 40%. Continuing to charge. Once sufficient chips are accumulated, the digester is approximately 70% full. The digester door is sealed. A mechanical lock is engaged, ensuring the door cannot open during the cooking process. The lock is operated by hydraulic pressure. Once engaged, the door cannot be forced open by any means until the internal pressure is reduced. An operator approaches the main control panel for the digester. This panel is the heart of the pulping operation. Multiple gauges display current temperature, pressure, and chemical concentrations. Digital displays show preset programs and current parameters. The operator makes adjustments with careful precision. The operator enters a preset cooking cycle, a program that has been refined over decades to produce optimal pulp quality. This program is not random. It's been developed through extensive research and thousands of previous cooking cycles. The program will control temperature, pressure, and chemical concentration throughout the approximately 3-hour cooking process. The pulping process begins. The operator presses the activation button. Systems come alive. Steam is injected into the digester at the bottom. The temperature begins to rise rapidly. The gauge shows temperature increasing: 40 degrees Celsius, 50 degrees, 60 degrees, 70. The steam is pressurized, creating heat with remarkable efficiency. The pressure in the digester begins to increase simultaneously. As temperature rises, the gaseous steam creates pressure that builds within the closed vessel. Simultaneously, chemical systems activate. Chemicals are injected into the digester through separate injection ports. These are primarily sodium hydroxide, caustic soda, and sodium sulfide. The chemicals dissolve in water distributed throughout the digester, creating a cooking liquor that surrounds the wood chips. The temperature continues to climb. 80 degrees, 90, 100. The pressure increases as the temperature rises. The gauge shows pressure increasing: 1 atmosphere, 2 atmospheres, 3 atmospheres. The digester is now operating at extreme conditions, high temperature and pressure that would be dangerous for humans but is essential for the pulping process. A worker monitors the pressure and temperature gauges constantly. Temperature at 115 degrees. Pressure steady at 3.2 atmospheres. Chemicals injected. System nominal. The worker reports into the radio. The chips inside the digester are undergoing a fundamental transformation. The heat penetrates the chips. The chemicals begin dissolving the lignin, the natural glue that binds the cellulose fibers in wood. The wood chips soften. They begin to break apart. The fibers start to separate. The cooking process is complex chemistry. The lignin dissolves in the alkaline chemical solution. The cellulose fibers, relatively resistant to the chemicals, remain largely intact. But the softening of the chips is dramatic. What was hard would become soft pulp. The pulping process takes approximately 3 hours from start to finish. During this entire time, the digester operates autonomously, controlled by the preset program. The operator monitors the progress continuously, watching gauges and reviewing printouts from sensors. Everything is recorded: temperature at each moment, pressure readings, chemical concentrations, timing. The data is essential for quality control. The cooking program advances through stages. The initial stage heats the chemicals and begins dissolving lignin. An intermediate stage maintains high temperature while the cooking liquor penetrates the chips. A final stage at even higher temperature completes the delignification process. Occasionally, the operator makes small adjustments. If pressure is slightly higher than expected, steam discharge is increased slightly. If chemical concentration is lower than anticipated, additional chemicals are injected. These adjustments are minor but important for maintaining precise conditions. After approximately 180 minutes of cooking, the temperature is slowly reduced. The pressure is released gradually through a controlled vent. The operator doesn't rush this process. Rapid cooling could cause the fibers to collapse or become damaged. Slow, controlled cooling, taking approximately 30 minutes, is essential for producing high-quality fibers. A worker monitors the pressure reduction. Pressure reducing. Now at 2.8 atmospheres. Continuing reduction. Temperature reduced to 105 degrees. The cooling is patient and deliberate. The digester cools gradually. As pressure drops, safety interlocks confirm that the internal pressure is safe. Once the internal pressure reaches atmospheric pressure, the digester door lock is released automatically. After 3 hours of cooking, the transformation is complete. What was solid wood chips has become pulp. The lignin has been dissolved and removed. The cellulose fibers, now separated, remain. The digester door swings open. Inside, instead of solid wood chips, the operator sees a dark brown slurry, a mixture of separated wood fibers and cooking liquor. This is called pulp. The color comes from residual lignin still present in the pulp. This brown pulp will be washed and cleaned in subsequent steps to remove the remaining impurities. The pulp is extracted from the digester by forcing it through a discharge valve at the bottom using pressurized water. The extraction is controlled. The operator manages the discharge flow to prevent overloading the collection system. The pulp flows into a large holding tank below. The slurry is dark brown and relatively thick, though still liquid. The water content is carefully controlled to maintain optimal consistency. The material is warm, still containing heat from the cooking process. Multiple digesters operate simultaneously at the pulping facility. As one completes its cycle and begins discharging, the next is entering its final cooking stages, and a third is beginning the charging process. The rhythm of the facility is established. Every 3 hours, one digester discharges its pulp. The pulp from the discharge tanks is transported via pipeline to the paper mill's next stage. The pulp begins its journey toward becoming paper. The dark brown liquid, so different from the white paper that will eventually result, represents the essential transformation. Fibers separated and ready to be reformed into new material. The cooking process is complex chemistry. The lignin dissolves in the alkaline chemical solution. The cellulose fibers, relatively resistant to the chemicals, remain largely intact. But the softening of the chips is dramatic. What was hard would become soft pulp. The pulping process takes approximately 3 hours from start to finish. During this entire time, the digester operates autonomously, controlled by the preset program. The operator monitors the progress continuously, watching gauges and reviewing printouts from sensors. Everything is recorded: temperature at each moment, pressure readings, chemical concentrations, timing. The data is essential for quality control. The cooking program advances through stages. The initial stage heats the chemicals and begins dissolving lignin. An intermediate stage maintains high temperature while the cooking liquor penetrates the chips. A final stage at even higher temperature completes the delignification process. Occasionally, the operator makes small adjustments. If pressure is slightly higher than expected, steam discharge is increased slightly. If chemical concentration is lower than anticipated, additional chemicals are injected. These adjustments are minor but important for maintaining precise conditions. After approximately 180 minutes of cooking, the temperature is slowly reduced. The pressure is released gradually through a controlled vent. The operator doesn't rush this process. Rapid cooling could cause the fibers to collapse or become damaged. Slow, controlled cooling, taking approximately 30 minutes, is essential for producing high-quality fibers. A worker monitors the pressure reduction. pressure reducing. Now at 2.8 atmospheres. Continuing reduction. Temperature reduced to 105 degrees. The cooling is patient and deliberate. The digester cools gradually. As pressure drops, safety interlocks confirm that the internal pressure is safe. Once the internal pressure reaches atmospheric pressure, the digester door lock is released automatically. After 3 hours of cooking, the transformation is complete. What was solid wood chips has become pulp. The lignin has been dissolved and removed. The cellulose fibers, now separated, remain. The digester door swings open. Inside, instead of solid wood chips, the operator sees a dark brown slurry, a mixture of separated wood fibers and cooking liquor. This is called pulp. The color comes from residual lignin still present in the pulp. This brown pulp will be washed and cleaned in subsequent steps to remove the remaining impurities. The pulp is extracted from the digester by forcing it through a discharge valve at the bottom using pressurized water. The extraction is controlled. The operator manages the discharge flow to prevent overloading the collection system. The pulp flows into a large holding tank below. The slurry is dark brown and relatively thick, though still liquid. The water content is carefully controlled to maintain optimal consistency. The material is warm, still containing heat from the cooking process. Multiple digesters operate simultaneously at the pulping facility. As one completes its cycle and begins discharging, the next is entering its final cooking stages, and a third is beginning the charging process. The rhythm of the facility is established. Every 3 hours, one digester discharges its pulp. The pulp from the discharge tanks is transported via pipeline to the paper mill's next stage. The pulp begins its journey toward becoming paper. The dark brown liquid, so different from the white paper that will eventually result, represents the essential transformation. Fibers separated and ready to be reformed into new material. The paper mill has been quiet during the day while maintenance crews conducted their daily inspections and performed routine maintenance. But now, as evening approaches, the massive paper machine is being prepared for the night shift operation. The sounds will intensify dramatically, but they will establish a rhythm that defines the entire facility. The paper machine is one of the most impressive industrial machines ever created. It stretches over 100 meters in length and is approximately 5 meters wide. It's a complex assembly of rollers, screens, presses, and dryers. It exists to perform one essential function: transform liquid pulp into solid paper. An operator with 15 years of experience takes his position before the massive control panel. This panel has hundreds of buttons, switches, digital displays, and indicator lights. The operator knows this machine intimately, every sound, every vibration, every operational parameter. He's worked on this machine nearly every day of his career. The operator performs a comprehensive startup checklist. He begins at the top of the sheet and works systematically downward. Every system must be verified before the machine starts. Check water supply pressure. He moves to a gauge. The pressure is normal, 2.5 atmospheres. Water supply confirmed. He marks the checklist. Check hydraulic system pressure. Multiple gauges show hydraulic pressures throughout the machine. All are within normal range. Hydraulic systems confirmed. Verify safety interlocks engaged. He presses test buttons that verify safety systems are functioning. All interlocks engaged. Confirm chemical dosing systems ready. The operator reviews chemical tanks for size press application, coating materials if used, and other chemical systems. Chemical systems ready. Verify forming fabric tension and condition. He inspects the forming fabric, the crucial fine mesh screen that forms paper. Fabric condition acceptable. Tension within specification. The checklist is long and detailed. Nothing can be overlooked. A malfunction during operation could damage the machine or endanger workers. The checklist takes approximately 30 minutes to complete. The operator activates the system. The background machinery powers up. Pumps begin running with a hydraulic whine, compressors engage with compressed air hissing, hydraulic systems pressurize with a steady rising sound. The sound is complex. Multiple systems operating simultaneously, creating a subtle rumble underlying everything. Lights throughout the paper machine activate. The machine is now energized, ready to operate. The operator makes final visual checks, walking along the machine, observing that everything is functioning correctly. Water is flowing. Hydraulic lines are pressurized. Electrical systems are active. The operator returns to the control panel. He performs final digital system checks, reviewing the startup procedure on the panel's main display. Everything shows green, all systems ready. The first critical step is adjusting the pulp consistency. The pulp arriving from the holding tanks is extremely dilute, perhaps 1% fiber and 99% water. For paper making, the pulp must flow at the optimal consistency. The consistency must be adjusted carefully. Dilute pulp doesn't form paper, concentrated pulp flows too slowly and unevenly. A worker at a consistency tank adds clean water to the pulp. The flow rate is controlled by a precision valve. Water flows in smoothly, reducing the pulp concentration. Another worker monitors a consistency sensor that measures pulp concentration in real time. The sensor provides a digital readout showing current percentage solids. As the consistency approaches the target, approximately 0.3% fiber, the valve is adjusted to maintain that level continuously. The adjustment is automatic through a feedback control system. If concentration increases, water is automatically added. If it decreases, the water supply is automatically reduced. The system maintains the target consistency with remarkable precision. The pulp is now prepared and flows toward the paper machine's head box, the starting point of the paper-making process. The head box is essentially a pump and flow control system. It distributes the pulp evenly across the entire width of the paper machine. The head box operator monitors flow rates and makes fine adjustments to ensure uniform distribution. The operator makes final adjustments at the main control panel. The head box flow rate is set. The pulp begins to flow toward the forming fabric, a fine mesh screen that's part of the paper machine's working surface. The operator watches pressure gauges. All systems are functioning normally. The operator takes a deep breath and presses the start button. The paper machine begins to run. The enormous machine comes to life. The forming stage is where magic happens. Liquid pulp becomes solid paper in a series of steps that take less than a second per meter of paper length, yet the forming section of the machine stretches for over 30 meters. The dilute pulp flows from the head box onto the forming fabric, a moving screen made of fine synthetic fibers. The fabric moves at high speed, initially around 300 meters per minute. This is fast, approximately 5 meters per second. As the pulp lands on the moving fabric, water immediately begins to drain through the screen. The moment the pulp touches the forming fabric is critical. The fibers land on the screen randomly at first, but as water begins draining, the fibers start to interlock. Fibers that land close to each other begin to bond. The random arrangement gradually becomes more organized as the fibers bond together. The paper structure forms. Suction boxes beneath the forming fabric pull water downward through the screen with tremendous force. The sound is a steady, rhythmic whoosh as water is extracted. The water flows through the drainage system and is collected. Some of this water will be recycled back into the pulp preparation system, making efficient use of water. As the fibers lose water, they begin to bind together more firmly through hydrogen bonding, a natural physical process that requires no additional chemicals. The water removal triggers this bonding process. What was liquid pulp is becoming solid. As the pulp-laden fabric moves along the forming stage, additional suction boxes continue removing water. The fibers become progressively bonded. The paper is literally forming itself as water is removed. The forming fabric moves forward through the forming stage. The first 5 meters, water begins draining. The fibers are still relatively mobile. They begin to align with the flow of remaining water. The paper is weak. If you tried to lift it now, it would fall apart immediately. The second 5 meters, more water is removed. The fibers are becoming more bonded. Approximately 60% of the water has been removed. The paper is gaining strength, though still fragile. The third 5 meters, suction intensity increases. The remaining water is removed more aggressively. The fibers are now bonded quite firmly. The paper has developed sufficient strength that it could be lifted gently without tearing. The fourth 5 meters, final suction removes the last of the water that can be mechanically removed. The paper now contains perhaps 60% water, still very wet, but it's now a recognizable, cohesive sheet. The final 5 meters, the paper passes over a flat suction box that ensures uniform drainage across the entire width. Any uneven areas are smoothed as water is removed evenly. After approximately 30 seconds of forming, what was once slurry has become paper. It's still extremely wet, containing perhaps 60% water, but it's now a recognizable sheet of paper with discernible thickness and structure. The transformation is remarkable. As the forming fabric and its attached paper move forward, they approach a critical transition point. The paper must now be transferred from the forming fabric to a pressing system. This transfer must be done carefully to prevent tearing. The pressing stage is where mechanical force removes the remaining water from the wet paper. The paper is still fragile at this point, but it's strong enough to withstand significant pressure without tearing. The pressing section stretches for approximately 20 meters. The paper, still on its supporting forming fabric, approaches the first press roller. This is an enormous steel cylinder, approximately 2 meters in diameter and 5 meters wide. Behind the paper, positioned directly opposite, is another massive roller, a press roll that will apply force from above. The space between these two rollers is called the press nip, the location where tremendous pressure will be applied. The width of the nip is only approximately 10 to 15 millimeters, but the force is enormous. Multiple hundred tons of force will be concentrated across this narrow space. The paper approaches the press nip. Operators monitor the alignment carefully. The paper must enter the nip squarely, or uneven pressing will result in thickness variations. The paper advances into the nip. What happens next is dramatic. The pressure is applied suddenly. The paper passes through the press nip. The water is squeezed out of the paper with mechanical force. It flows away as waste discharge. The sound is a deep, metallic compression, a satisfying squeeze as water is expelled from the fibers. The paper emerges from the first press roller dramatically drier. Its wet weight has been reduced. The fibers are compressed together more tightly. The paper's strength increases significantly. What was fragile before pressing is now significantly stronger. The paper continues forward to additional press rollers. Most paper machines have 5 to 7 press rollers in sequence. Each successive press removes additional water. The first press removes the most water, perhaps 40% of what remains. Subsequent presses remove smaller quantities. As the paper passes through each press, its character changes. The first press, the paper is flattened and compressed. The second press, fibers are bonded more tightly together. The third press, the paper becomes denser. By the fifth press, the paper has lost perhaps 80% of its remaining water. Workers monitor the paper as it exits each press. They look for proper formation, even thickness, and freedom from tears or defects. A worker stands between the third and fourth press with a thickness gauge. As paper passes through, he periodically places the gauge on the paper surface, measuring thickness. The reading should be consistent, approximately 150 micrometers for standard copy paper. Paper thickness consistent. Pressing normally, the worker reports into his radio. The pressing section produces tremendous heat through mechanical friction. The fibers are compressed and heated simultaneously. This combination of pressure and heat further bonds the fibers together. After passing through all the press rollers, the paper has been pressed to its final wet condition. It still contains approximately 10% water, necessary for the next stage, drying, but it's now a strong, cohesive sheet that can be handled safely. The supporting fabric is separated from the paper through a clever mechanical arrangement. The fabric wraps around a roller, naturally separating from the paper. The paper, now freestanding, is transferred to the dryer section of the machine. The drying section is the largest and most visually impressive part of the paper machine. It consists of dozens of heated rollers arranged in multiple tiers, sometimes up to 7 or 8 levels stacked vertically. The sight of hot paper moving through a forest of rollers is mesmerizing. The paper is transferred onto the first heated roller. These rollers are heated internally by steam, reaching temperatures of approximately 120 to 130 degrees Celsius. The paper, moving at the same speed as the rollers, approximately 300 meters per minute, comes into contact with the hot surface. The remaining water in the paper begins to evaporate immediately upon contact with the hot roller surface. Steam rises from the paper surface. The sound is a continuous, gentle hissing, the sound of water transforming from liquid to gas. The moisture content of the paper drops rapidly as it moves across the roller. What was 10% water becomes 5% within seconds. But the paper doesn't rest on each roller for long. The machine moves quickly. The paper is transferred from the first roller to the second roller, often by an intermediate fabric or guide. The second roller is also heated. More heat, more evaporation. The sound continues, a soft, rhythmic hissing that repeats with each roller. The paper gradually dries as it passes through the machine. The transformation is continuous. Workers walk alongside the drying section, monitoring the operation. A quality control technician carries a handheld moisture meter. He periodically reaches toward the moving paper, carefully and safely, and touches the meter to the paper surface briefly. The meter displays the moisture content. Initial check, exiting press, 10.2% moisture, he records. As the paper advances through the dryers, after first roller, 7.5%. After fourth roller, 4.8%. After eighth roller, 4.1%. The moisture is decreasing at a steady rate. The drying is carefully controlled. If the paper is dried too quickly, internal stresses develop that can cause the paper to break or curl, a condition called picking. If it's dried too slowly, the machine's throughput is reduced and energy costs increase. The optimal drying rate is maintained through careful temperature control of the rollers and the speed at which the paper is fed through. The drying section is engineered to manage heat efficiently. The rollers are heated by steam, the same steam produced by the biomass power plant that burns mill waste. The steam circulates through internal passages inside each roller, transferring heat to the roller surface. As steam condenses, it releases its energy to the paper. This is an efficient energy transfer method. The paper continues through successive rollers. The drying becomes progressively more effective. The first 5 rollers remove the bulk of the water. Subsequent rollers remove residual moisture. By the time the paper exits the drying section, it has essentially reached its target moisture content. A worker walks alongside the final dryer rollers. He carries a handheld moisture meter, which he uses to verify that drying is proceeding correctly. Final check: 4.1% moisture. Target is 4.0 to 5.5%. Excellent consistency. The moisture meter reading is critical. The optimal moisture content for paper is approximately 4 to 5%. At this moisture level, the paper is strong, flexible, and stable. Too dry, below 4%, and the paper becomes brittle. Too moist, above 6%, and the paper's strength is compromised. The sound of the dryer section, the hissing of steam and the quiet rumble of rollers, is mesmerizing. The sight of steam rising from the paper creates an ethereal, almost mystical atmosphere. The continuous motion of paper through the drying zone, combined with the constant steam, creates a hypnotic visual effect. After passing through approximately 10 to 12 heated drying rollers, the paper has reached its target moisture content. The paper is now dry, or more accurately, it's reached its equilibrium moisture content where water content is neither increasing nor decreasing. The fibers are essentially locked into their final position. The paper's feel and sound change. It becomes crisper, more papery, less pliable. The paper emerges from the final drying roller in a long, continuous sheet. It's smooth, uniform, and ready for the next stage. The sound of the dryer section, the hissing of steam and the quiet rumble of rollers, begins to fade slightly as the paper moves toward the calendar section. The paper now passes through the calendar section, a series of smooth, hard rollers that compress the paper's surface. The goal is to create a perfectly smooth, uniform surface suitable for printing. This stage is critical for print quality. The calendar rollers are harder than the dryer rollers and run at slightly higher pressure. As the paper passes between them, the surface is compressed and smooth. Microscopic irregularities, small bumps and valleys on the paper surface, are pressed flat. The paper's surface becomes increasingly smooth and uniform. There are typically 3 to 5 calendar rolls. The first calendaring pass removes the largest surface irregularities. Subsequent passes create progressively smoother surfaces. A worker monitors the paper's surface gloss as it exits each calendar roll. He uses a gloss meter, a handheld device that measures the reflectivity of the paper surface. Post first calendar, gloss reading 65. He records the number. Post second calendar, gloss reading 72. Post third calendar, gloss reading 80. A perfectly smooth, glossy surface has been created. 4 coated papers. This is where coating materials might be applied. But for uncoated papers like those in this facility, the natural surface smoothness is the goal. The calendar section achieves this through mechanical compression. The paper emerges from the calendar section with a smooth, uniform finish. The transformation is dramatic. The paper has changed from rough and porous to smooth and dense. If it's coated paper, it has a glossy finish. If it's uncoated, it has a smooth, clean finish suitable for printing. The final stage in the paper-making portion of the machine is sometimes a super calendar, an additional polish that creates exceptional smoothness. But our facility produces a range of paper grades, so not all paper passes through the super calendar. The finished paper is now perfect. It's ready to be wound onto a large roll. A massive winding mechanism stands ready. This device will accumulate the thin paper sheet onto a large wooden core, creating what's called a parent roll. The finished paper is guided to the winding station. An automated mechanism positions a large wooden core, a cylindrical tube approximately 2 meters in diameter made of dense wood. The core is mounted on two support structures that allow it to rotate freely. As the paper approaches, a mechanical grip positions the leading edge of the paper onto the core. The winding mechanism begins to rotate. The paper is wound onto the core layer by layer. The winding process is automatic and continuous. The core rotates at the same speed as the paper, preventing any tension or wrinkles. Sensors monitor the paper throughout the winding, looking for misalignment or defects. If any are detected, alarms alert operators. The paper accumulates on the core layer by layer. The roll grows larger. 5 centimeters of paper has been wound, then 20 centimeters. By the end of the winding process, the roll has accumulated hundreds of layers of paper, creating a massive cylinder approximately 2 meters in diameter and weighing several tons. The winding station produces a gentle whirring sound as the core rotates. The paper feeds smoothly onto the roll. The operator watches the winding progress on a display screen. The diameter of the roll is calculated continuously as more paper is wound. Current roll diameter, 80 centimeters. Estimated completion in 4 minutes. The roll grows to its final size. Typically, each roll contains approximately 300 to 400 kilograms of paper, depending on paper thickness. The operator verifies that the final roll diameter is correct. The winding is stopped. A mechanical device releases the roll from the winding station. An overhead crane positions itself above the roll. The crane's hooks engage with specially designed attachment points on the roll's wooden core. The crane lifts the massive roll, several tons of paper, and positions it on a roll cart. Multiple rolls are produced each hour. Each roll is identical, the same paper quality, thickness, and weight. The rolls are transported from the winding station to the paper storage area using the roll carts. Workers push the carts, positioning the rolls on storage racks designed to hold multiple rolls. The storage area is impressive. It contains dozens of rolls, each one representing hours of production. The rolls are organized by paper grade and production date. A quality control team periodically inspects samples from stored rolls, verifying that paper quality is consistent throughout the production run. The paper machine operates 24 hours a day, 7 days a week. The sounds continue without interruption. The machinery operating, steam hissing, rollers rumbling. Paper is being produced continuously, even during night shifts when fewer workers are present. While the paper machine operates continuously, another process is preparing to transform this paper into finished printed products. The printing facility adjacent to the paper mill is awakening with its own distinct rhythms and sounds. The printing manager reviews today's production schedule. A detailed document outlines what will be printed. A magazine with 4-color process printing. 20,000 copies are scheduled. The magazine consists of 48 pages, created by folding and binding large sheets. The printing manager walks through the printing facility. This is a substantial operation. The facility contains multiple printing presses, each one capable of producing thousands of sheets per hour. The presses are arranged logically. The most recent technology is positioned near the paper storage area, creating an efficient workflow. The printing room for today's job is prepared. Today's magazine will be printed on 4 separate press units, each applying one color. The color sequence is critical in offset printing. Typically, the process is cyan, magenta, yellow, and black, the CMYK color model. The first preparation step is ink formulation. Printing inks are not simple paint-like substances. They're complex chemical formulations with specific properties. The ink must have the correct viscosity, thickness, proper adhesion to paper, the right drying time, and exact color specification. An ink technician approaches the first ink formulation station. He's preparing cyan ink, the vibrant blue color that will be the first to print. He consults a formulation recipe on a document. The recipe specifies cyan pigment 400 grams, ink vehicle 1 liter, and various additives. The technician measures each component with precision. The cyan pigment is a fine powder, an organic chemical that provides the blue color. He places it on a precision scale and measures exactly 400 grams. 400 grams of cyan pigment measured, he records. The ink vehicle, a complex liquid made of oils and resins, is measured next. 1 liter of vehicle measured. Various additives are added in small quantities. Wetting agents that help the ink flow properly, anti-foaming agents that prevent bubbles, and drying accelerators that ensure the ink dries at the correct speed. All components are placed in a mixing vat. An automated mixer, an apparatus with rotating paddles, begins to blend the components. The mixer operates slowly at first, ensuring all components are mixed. The cyan pigment gradually disperses into the vehicle, creating a uniform blue liquid. The mixing continues for approximately 30 minutes. The resulting ink is smooth, uniform, and perfectly formulated for the printing process. The color is verified by comparing the ink to a color standard under controlled lighting. The match must be exact. Color consistency is critical for print quality. The finished cyan ink is transferred to containers, large quantities of ink that will be transported to the first printing press's ink fountain. Simultaneously, at other stations, magenta, yellow, and black inks are being prepared following identical procedures. The magenta will be a vibrant red-purple. The yellow will be bright and intense. The black will be deep and rich. 4 perfectly formulated inks will be ready to begin the printing process. The moment approaches when the first printing will begin. All preparation is complete. Paper is available. Inks are formulated and ready. The printing press has been adjusted for the paper size and specifications required for today's magazine. A technician positions the first sheet of paper in the press's feed mechanism. This is the moment before production starts. The press is now fully prepared, plate mounted, ink loaded, paper ready, press clean and functioning. The operator takes his position at the main control panel. He's been working with this press for 12 years. He knows its characteristics, its capabilities, and its quirks. His hands are positioned over the controls. He takes a deep breath. The operator presses the start button. The press comes to life with a dramatic change in sound. The background machinery sound, which was relatively quiet, suddenly increases. The paper feed mechanism engages with a distinctive mechanical whirring sound. The sophisticated mechanical and electronic systems that control the press activate. Hydraulic systems pressurize. Electrical motors spin. Air pressure increases in pneumatic systems. The entire press is coming alive simultaneously. The sound is industrial and powerful, but there's a rhythm and precision to it. The operator listens carefully, monitoring the sounds. His experienced ear can detect any anomaly. A sheet of paper is automatically fed into the press from a large stack by mechanical fingers. The sheet is gripped carefully, not damaged but firmly held, and conveyed forward into the printing unit. The paper advances through the press. The printing plate, covered with cyan ink, comes into contact with the paper surface. The image is transferred from the plate to the paper in a process called offset printing. The paper emerges from the first color station marked with cyan ink. The image is visible but incomplete. Color printing requires all 4 colors to create a complete color image. The sound of the printing press is complex. Each paper feed makes a distinctive clack 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 sound as the automatic gripper releases a sheet, grips a new sheet, and advances it. The sheet contacts the printing plate with a soft impression sound. The ink transfer creates a sound like paper slightly sliding. The sheet is released onto the output conveyor with a gentle placing sound. The paper immediately advances to the second color station. The second plate, carrying the magenta color, comes into contact with the paper. The magenta image is printed in registration, perfectly aligned with the cyan already on the paper. This registration is critical. Even a misalignment of 0.5 millimeter will result in visible color fringes that make the printed image appear blurry. The ink fountain keeps the magenta plate supplied with fresh ink. The ink transfer system ensures the correct amount of ink is applied to the plate. Too much ink results in heavy, muddy colors. Too little results in light, washed-out colors. The balance is critical and is maintained by sophisticated inking equipment. The paper advances to the third station. Yellow is applied. The third color is now on the paper. The image is becoming more complex. Blue and purple and yellow regions are visible, though still incomplete. Instantly, the paper is transferred to the fourth station where black is applied. The black provides depth and definition to the image. The combination of cyan, magenta, yellow, and black creates the full color image. All four colors are now on the paper. The image is complete. A full color picture or graphic is visible. The finished sheet exits the press onto an output conveyor. It joins other sheets coming through the same line. The sheets are stacked in precise piles by mechanical arms for later finishing. The press operates at remarkable speed, approximately 5,000 sheets per hour. Each sheet moves through all four color stations within seconds. The automatic feed, the precise plate contact, the instant color layering, the entire process is coordinated by electronic controls operating at computer speed. But the sound is distinctly mechanical. The rhythm never wavers. Clack, clack, clack. Feed, print, release, feed, print, release. The pattern repeats indefinitely, thousands of times per hour. Hours pass. Thousands of sheets are printed. The operator periodically stops the press for quality checks. He removes a printed sheet carefully and examines it under bright lighting. He's looking for printing defects, color shifts, misregistration, ink marks outside the intended area, or paper tears. He measures the sheet with a gauging tool. The color density is checked with a color spectrophotometer. The sheets are perfect. The press is operating optimally. The operator adjusts the inking system slightly, a minor adjustment to maintain perfect color consistency as the press continues running. The adjustment is made automatically through electronic controls that monitor feedback sensors. The press continues. More sheets are printed. The rhythm is hypnotic. The operator barely thinks anymore. His hands move automatically, monitoring systems, making tiny adjustments, ensuring consistency. By the end of the 8-hour print run, 20,000 sheets have been printed. The press is powered down. The printing is complete. The accumulated sheets, stacked on pallets, await the finishing stages. The printed sheets are transported to the finishing facility. Here, the simple sheets will be transformed into finished magazines through folding, cutting, collating, and binding. The first finishing step is folding. A massive folding machine stands ready. This machine is mechanical, not digital. Gears and cams control the folding process with perfect precision. A worker positions a large stack of printed sheets into the folding machine's feed hopper. The machine automatically pulls sheets from the hopper, one at a time. Each sheet is guided through a series of folding plates. The first fold creates a crease down the center. The sheet passes through mechanical fingers that bend it exactly in half. The sound of the folding machine is a distinctive rhythm, a clack 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 sound as sheets are grabbed by mechanical fingers, folded, and released. The rhythm is perfectly regular. Dozens of sheets per minute are folded by the machine. The operation is tireless and consistent. The folded sheets emerge from the machine stacked in neat piles. Each sheet is now half its original size, folded precisely in the center. 4 magazines with multiple nested pages, the sheets are fed through the folding machine multiple times, creating a more complex fold structure. After folding, the sheets move to the cutting stage. A cutting machine with a sharp, precise blade cuts the folded sheets to their final size. The blade descends with controlled force, enough to cut cleanly but not so much as to damage the paper underneath. Stack after stack is trimmed. The cut edge is perfectly straight. The precision is remarkable. Stack 1 completed. Dimensions verified. Moving to stack 2, a worker reports. The operation continues. 4 magazines requiring binding, the sheets are moved to the collating and binding station. Here, the individual folded signatures, that's the technical term for folded sheets, are collated in the correct order and then stapled together in the center. An automated collating machine places sheet on top of sheet in precise sequence. The machine has multiple feed stations, each holding a different signature. The machine can collate up to 36 different signatures, creating complex, multi-section publications. Sensors verify that each signature is correctly positioned. If a signature is missing or misplaced, the machine detects the error and stops. An operator addresses the problem, and the machine resumes. Once the correct number of signatures is collated, for a 48-page magazine, this might be 12 signatures of 4 pages each. The collated stack is moved to the stapling mechanism. This machine inserts staples into the center fold, binding the entire publication together. The staples are driven through the fold with precision. 2 or 3 staples hold the pages together securely. The bound magazine falls from the machine onto a conveyor. It's now a finished product, ready to be boxed and shipped to distribution centers. The finishing facility operates continuously throughout the shift. The sounds are rhythmic and predictable, the clack of folding machines, the sharp snap of cutting blades, the metallic clang of stapling mechanisms. These sounds, combined with the constant rumble of conveyors, create an industrial symphony. As finished magazines accumulate, quality control becomes critical. The facility cannot ship magazines with defects. Inspection is continuous and thorough. An inspector examines finished magazines as they exit the finishing line. She's looking for binding defects, page alignment issues, overall quality. She samples approximately 1 magazine per 100 produced. If all samples pass inspection, the entire batch is approved for packaging. If defects are detected, the press is stopped, and the problem is corrected. She opens a magazine, examining the binding. The staples should be straight and centered. The pages should be aligned correctly. She checks that all pages are present and in correct order. She closes the magazine and examines the external appearance. Everything checks out. Batch 1000 through 2000 approved for packaging, she reports. The approved magazines are transported to the packaging area. Here, magazines are counted, stacked, and boxed for shipment. The counting is automated. An electronic counter tracks the number of magazines, and when a box is full, typically 250 magazines per box, the machine signals that the box is complete. The filled boxes are sealed with automatic tape applicators. Labels are applied indicating the box contents, destination address, and other shipping information. The labeling process is automated, with barcodes encoding all necessary shipping information. The labeled boxes are stacked onto wooden pallets by forklift operators. Each pallet holds 60 to 80 boxes. The loaded pallets are positioned in the shipping warehouse, organized by destination for efficient loading onto trucks. As the papermaking and printing operations continue, other critical plant functions operate in the background. The facility's sustainability depends on efficient resource management and waste utilization. The bark removed during debarking, hours ago in our journey, has been transported to the biomass power plant. Here, the bark and other organic waste are burned in a controlled furnace. The combustion is carefully managed to maximize energy production while minimizing emissions. The furnace operator monitors temperature and combustion. Fuel is fed into the furnace at a controlled rate. Air is supplied at optimal levels for complete combustion. The temperature inside the furnace reaches approximately 900 degrees Celsius. The heat generated by burning the biomass is captured. Water circulates through the furnace walls, absorbing heat. The heated water becomes steam. The steam is pressurized and transported throughout the facility through an extensive piping system. The steam is essential to the mill's operations. It heats the digesters during pulping. It powers the drying rollers in the paper machine. It provides process heat for various other operations. By using waste biomass to generate this steam, the facility reduces its dependence on external energy sources. The biomass power plant generates approximately 70% of the steam required by the mill. The remaining 30% comes from a natural gas-fired boiler that provides supplemental capacity during peak demand periods. Water is another critical resource. The paper mill uses substantial quantities of water for pulping, washing, and cooling. To manage this sustainably, the facility recycles water whenever possible. Wash water from the pulping stage is treated and reused in later washing stages. Instead of discarding this water, it's collected, treated to remove the most concentrated impurities, and recycled back into the process. This reduces the volume of fresh water required. Cooling water is passed through cooling towers where air evaporation reduces its temperature, and it's reused for subsequent cooling operations. The cooling towers create visible steam on cool mornings. This is just water evaporating to reduce temperature. A water treatment facility manages the discharge water. Water that cannot be reused must be treated to remove contaminants before being released to the river. Treatment includes mechanical filtration to remove solid particles, biological treatment to remove dissolved organic compounds, and chemical treatment to adjust pH and remove other contaminants. A technician at the water treatment facility monitors treatment system performance. He checks chemical tank levels. He verifies that biological treatment systems are operating. He tests discharge water quality. Discharge water analysis, pH 7.2. Suspended solids, 12 milligrams per liter. Within acceptable parameters, he reports. The treated water is clean enough to be released to the river with environmental responsibility. Some of this treated water is also recycled back into the mill's water system, further reducing fresh water consumption. As the daylight fades, the facility transitions to evening operations. The paper machine continues running. It never truly stops. Paper is being produced continuously, even as the printing operation concludes for the day. Maintenance crews arrive for their evening shift. They perform routine maintenance on the equipment, checking bearings, adjusting tension on belts, cleaning components, and replacing filters. This preventive maintenance ensures that the machinery continues running reliably. A maintenance technician approaches the paper machine. He's checking the forming fabrics, the fine mesh screens that form the paper. These fabrics experience enormous stresses and wear continuously. They typically last 3 to 4 months before replacement. The technician examines the fabric carefully. He's looking for tears or excessive wear. The fabric appears healthy, continuing to perform well. He records his inspection in the maintenance log. In the mechanical room, a technician inspects the hydraulic systems. He checks fluid levels, looking for leaks or contamination. The hydraulic fluid is critical. Any degradation would impact equipment performance. The fluid level is correct. No contamination is evident. Hydraulic system nominal, he records. The evening shift brings a different character to the facility. There are fewer people. The supervisors are gone. The focus shifts from producing maximum volume to maintaining equipment reliability. Night operations continue through midnight and beyond. The facility is a 24-hour operation. As one shift ends, the next begins. Workers arrive to take their positions. The operations continue without interruption. As we complete our 130-minute journey through this integrated paper and printing facility, it's worth reflecting on what we've witnessed. We've seen wood from sustainable forests transformed into paper through chemical processes and mechanical pressing. We've seen that paper transformed into printed products through precise color application and mechanical finishing. The facility employs over 400 workers. It produces approximately 120 tons of paper daily. It prints and finishes hundreds of thousands of individual pieces. Magazines, catalogs, promotional materials, packaging, every single day. The environmental responsibility of such an operation is significant. Modern paper mills are far more efficient and cleaner than mills from previous generations. Technology has improved continuously. Energy consumption has decreased. Water usage has declined. Environmental impact has been reduced dramatically. The biomass power plant, burning waste from the papermaking process, provides much of the facility's energy. This is a closed loop. Waste becomes energy. The water treatment systems ensure that discharge water is clean before being released to rivers. The recycling of water within the facility reduces the consumption of fresh water by nearly 60% compared to older mills. The forestry practices that supply the mill are sustainable. Trees are harvested according to carefully managed plans that ensure new growth. For every tree harvested, new trees are planted. The cycle is continuous and responsible. Walking through the facility at midnight, everything is operating at full capacity. The paper machine is producing paper that will become tomorrow's printed products. Workers are monitoring equipment, making adjustments, ensuring quality. The facility's heartbeat is steady and continuous. The sounds are our constant companion through this journey. The rumble of machinery, the hiss of steam, the mechanical rhythms of the printing presses and finishing equipment. These are the sounds of production, of industry, of transformation. What begins as wood becomes paper becomes printed products. The simple task of creating printed material, something we take for granted, involves hundreds of steps, millions of precise mechanical movements, complex chemistry, and careful human management. The industrial rhythm continues. Somewhere a paper mill is operating. Somewhere a printing press is printing. Somewhere machinery is moving, water is flowing, steam is rising. The rhythm is eternal. Sleep now to the gentle rhythms of industry. The facility continues. The machinery continues. The paper continues to flow.